So let's quickly see we have discussed the transmitter part, right? How to design a transmitter for any arbitrary signal space P1T as it is asked in the exam also, and also we have discussed particularly BPSK or phase shift keying in the last class, right? We have discussed PSK, SK, QM. So all this transmitter can be designed, right? How will you design the transmitter? Very easy. You will just, so let's take an example of BPSK. So 0 will be mapped with cos of 2 pi fct. 1 will be mapped with minus cos of 2 pi fct. And these are the factors or so 0 will be mapped with, and then you can write minus a with k times cos 2 pi fct. This will become your 5 phi t. Why I have used k? Just to make sure that this is unit energy, or you can just apply Gram-Smith and you will get that what is the value of k, etc. So this is will be k of phi t. So yeah. So you will map 0 with this value and 1 with this value, right? 0 with this value and 1 with this value, and you will multiply with the phi t and you will transmit it, right? This is what we have discussed in the last class. And or in general, what we have discussed in general, any two-dimensional PSK or COM signal, any COM signal or PSK signal, we can generate like this, where you have to take number of bits. For example, QPSK, how many bits you will take? 2 bits at a time. You will map it to the constellation points and accordingly you will transmit, right? This point is clear, correct? This is the transmitter part. Please ask if you have any doubt. This is phi 1t, this is phi 2t. This we have done in the last class. This part is called in phase part, and this is part called Q part. So for binary case or BPSK case, Q part is 0, right? As you can see, only cos part is there. There is no sign. So there we will put 0. Or in general, that is why we call that any SK or COM scheme, the transmitter can be designed from here. Bit streams are bit stream. This is your information source, which is by some logic you are converting it to bit streams, and then this logic is used, and then this is transmitted. This is called any general COM or PSK transmitter architecture. Just look at this value. A transmitter diagram. This is the transmitter for any PSK COM scheme, right? So what happens in the channel? So आपका क्या है pictorially what you are doing, Abhishek? You are transmitting one of the following points pictorially. Yes or no? For 4 case, we are taking 4 points 0 0 0 1 1 0 or 1 1 or 1 0. We have done arbitrary mapping. So what is happening? That you are transmitting one point at a time. Yes or no? This is called geometrical representation of your signal or constellation diagram. So just by looking at the constellation diagram, this is the way to generate your transmit signal. And for analytical understanding, you can just see this constellation diagram and quickly you can say when 0 0 is transmitted, you will transmit this much of phi 1t plus this much of phi 2t, right? For example, this is A and this is B or AI or AQ. So AI phi 1t plus AQ phi 2t. So this is the signal which you are going to transmit corresponding to 0 0. Similarly for others. Once this any of this will pass through the channel and you transmit a lot of such signals, or so at the receiver, what would happen? If the channel is perfect, perfect means no noise, no distortion, nothing. Everything is perfect. So what would happen? Whatever you transmit, you will receive, right? If you transmit this, you will perfectly receive this. Meaning, if you transmit AI phi 1t plus AQ phi 2t, you will receive same. But this is not the case in practice. Meaning that we encounter the noise. And how do we model the noise generally? Bolo Abhishek. How do you model the noise? Additive. क्या है noise? Noise is additive in nature, meaning that if you are transmitting this signal xt at the receiver, you will receive the RT, which is xt plus nt. So your noise is additive in nature. Mathematically, if we model it by saying that your signal is getting added with the noise. And practically, this noise is added at the front end of the receiver. How do you design the receiver if you remember? I told you, whatever you receive from the channel, whatever basis we have used at the transmitter, you will multiply it or pass it through integrator. This is called correlation filter. Bank of correlators, do you remember? Yes or no? Abhishek? So what is going to happen at the receiver end? What happens? आपके पास क्या होता है? Practically there is an antenna. If this is a wireless system, there is an antenna, there is a low noise amplifier, and then it is passed through these devices. So these are various hardwares which will introduce the noise. Inside the hardware, whatever you provide, the output is not always that. It is some due to the random fluctuation of the electrons inside that. What happens? The current in general, if you receive it, it will go in the form of a current. But at the output, there will be some fluctuated version due to the random fluctuation of noise. So we say that the noise is additive in nature. ठीक है. Next, what is the statistics of noise? अच्छा मुझे बताओ, if today you transmit xt and after some time you transmit xt, will the noise will be same? Or if you measure it here, okay, just don't give any signal here, for example, and just put your milliampere or the meter, the meter which I mean the output, measure the output, you will see fluctuations, right? You can never say what is the noise which is going to be added. It means noise is random. क्या है? Noise additive है. We have observed empirically that the noise is additive, or the practically we have observed that noise is additive, and we have also claiming that it is random. And of course it is random because you cannot say what is going to be the value. If we knew this value, we will just subtract it from RT and we will give XT. But we don't know the NT, right? Then what do we know about NT? Do you know anything about NT? By empirically measuring, or by measuring this called the hardware, we say the noise is Gaussian, or if it is a random process. Okay, so NT is a white process. क्या है? It is a white random process. What do we mean by white? If we plot its power spectral density, okay, Abhishek, do you remember if we wanted to see the frequency content of a signal, what we do? Fourier transform. But this is true when your AT is deterministic. When you know it's like uska formula pata hona, right? You know the formula that it is sine, cos, x square, something, right? You know how it is changing with time, right? And it is deterministic. Then only you can implement Fourier, right? Yes or no? But the random process, we don't know its nature. If you measure the noise for this duration, and again from this window, you take a window, you measure the noise. Noise can be anything. You cannot say what is the noise, right? So if you want to see what is the Fourier, what is the frequency content of this, you cannot take Fourier transform. But what you can do, you can evaluate its power spectral density by using its, I'm not, are you taking a statistical course? Abhishek, are you taking the statistical course? Okay, so I assume that you know a bit of that, but it is called power spectral density in order to understand the frequency content in it. And it is flat, means all the frequency content which are possible is available inside this, then it is called white. Because you know the white light, right? White light contains all the colors. So by that analogy, if there is something, there is a random process which has the frequency content, all the frequency content with same amount, as you can see, it is constant, right? So all the frequency content or the power spectral density is constant. Okay, I'm not going into deep, but what is noise here? Noise is additive and white. Okay. At the receiver end here, you will receive, I am assuming that this all the hardware is introducing some kind of noise, and you have transmitted xt and you have received xt plus nt here, right? Okay. Okay, then what would happen? It will pass through this, yes or no? So tell me what would be the output? Xt plus Nt. If you see the in phase part, this is called upper branch is called in phase part and the quadrature phase part corresponding to k times cos, k times sine. Now I am specifically discussing the receiver for the PSK and QAM, but it applies for others also, right? There it will not be cos sine but phi 1 and phi 2, which you can obtain using Gram Smith. Okay? Understood my point, Abhishek? Yes or no? Do you appreciate what I said or not? Okay. What is going to happen? This part, xt क्या है बताओ? xt is a signal from this constellation which will have some part of phi 1t and some of the phi 2t, right? It can be any point in the constellation, and I said I am talking about PSK QAM, so they are two-dimensional and there are only two bases, so all the points can be represented as a linear combination or weighted summation of phi 1 and phi 2. So my xt is this, where ai and aq can be depending upon the point which you are transmitting, right? Do you appreciate that or not? Let me know if there is some doubt. So what would happen? The upper branch, you will pass it through phi 1t. Yes, Abhishek? So क्या होगा output? Branch, upper branch. What will you get? ai phi 1t square dt plus aq phi 2t phi 1t dt plus nt phi 1t dt. Yes or no? तो मुझे बताओ इसका आंसर क्या? व्हाट वुड बी द आंसर? बाय यूजिंग द प्रॉपर्टी ऑफ ऑर्थोनॉर्मल बेसिस, दिस इज 0 and this is 1. Yes or no? So you will get ai plus this part. So this will give you some fixed value w. Yes or no? This is a function. This is a function. You integrate it from 0 to t. You will get some value, right? Because it's a integral, right? And the limit are there. So it's a definite integral. Therefore, you will get some value. So at the output here, what will you get? You can also call it yi, ai plus wi, and here you will get aq plus wq. But what do you know about wi and wq? You just know that this is a wide process with power spectral density n naught by 2, right? So what happens? These samples which we collect, they are value wi here, wi and wq. I am not going much into detail, are Gaussian with mean 0 and variance n naught by 2. ठीक है? Where wi is this and wq क्या हो जाएगा? Similarly, wq is the noise which goes to the lower branch of the receiver, right? Or the quadrature branch of the receiver, 0 to t, where nt is white with power spectral density n naught by 2. There are some more assumptions that each of this, anyway, so that we are not going in that detail, but the nature I mean, when I write like this, what do I mean? Can anyone tell? Can anyone just tell me a few words, because you are doing various courses? I just said that it is normal or Gaussian with any. Okay, just Abhishek, यहाँ तक clear है? Do you, I mean, are you comfortable till this point? Okay, so here we are going to discuss that what is this. See, at every time you pass it, this Wi will be a random value that you appreciate or not. Because the NT is random itself, of course it's integral, because this is not, this is random, so this will be random, right? Yes or no? See, for example, you transmit this point, there will be some noise. After some time you transmit the same point, there will be some noise, or you transmit this point, there will be some noise, right? But the noise is different. You cannot predict it because it depends upon the hardware, and hardware, inside hardware, what is happening you don't know, right? This is random fluctuation of electron which you are modeling. ठीक है? Yes or no? Short noise, etc. that you can see. So if this function you don't know what is the value of this NT, it can be this, it can be this, it can be this, right? Of course integral will be different, but what you know that your W will have some okay, so repeat this experiment 1000 times. Repeat this experiment, you just measure the noise 1000 times or 10,000 times, find this integral and make a histogram. Histogram everybody knows? Yes or no? So the question is how if this is W, which you are evaluating this integral again and again and again and again, and what you observe that for some time, most of the time the value is 0, but with some other time it can be this, it can be this, it can be this, it can be this, but most of the time this W will have this value which is called its mean, and it is spread depending upon its value n naught by 2. If n naught by 2 is more, it means variance is more, it will be more spread, and if n naught by 2 is less, means your hardware is good, the noise is not very much, so it will be centered around 0. There is not much problem with your hardware, right? That you can say in layman terms. You understood now? So most of the time it is centered around origin, but depending upon this value n naught by 2, so this is called Gaussian distribution. क्या बोलते हैं इसको? What do you call it? Gaussian distribution. What are the, and how do you represent it? Like this. W is Gaussian with mean, mu and variance. Sigma square, in our case, mean is 0 and sigma square is n naught by 2. So our case, mean is 0 and variance is sigma square. So do you have the form expression for its PDF? इसको क्या बोलते हैं? Probability density function, right? All of you know that from the statistical course. Yes or no? So what is the PDF of? So what I said here, that this part is random, but what do I know about this part is that it is centered around 0, but depend upon the n naught by 2, its variance depend upon the, or its spread depend upon the n naught by 2, and we call, this is called PDF of a normal distribution or a Gaussian distribution with mean, mu and variance sigma square evaluated at some point W. What do I mean by that? this is W. So you can assume that this is a function of W. What is the value of this function at some W? 1 upon root 2 pi sigma square exponential of minus W minus mu whole square divided by 2 sigma square, where W is from minus infinite to infinite. ठीक है, अभी क्लियर हो गया? This is mean and this is its spread is governed by the variance. Yes or no? I mean, is it clear to you? This is the PDF. What is the PDF? Of a normal or Gaussian distribution with mean mu and variance sigma square evaluated at W, you have to apply this formula. If W is 2, for example, you can put W2 here and you will get some value. You can see what are the probability density function of this evaluated at this point. Are we clear? Yes or no? By नॉइज फिगर हमेशा कैलकुलेट करके देखते हैं कि व्हाट इज द अप्रॉक्सीमेट पावर स्पेक्ट्रल डेंसिटी फॉर कम्युनिकेशन. फॉर एग्जांपल द इट इज अराउंड -144 dBm. ये हार्डवेयर का क्वालिटी है, मतलब इट इज फिक्स्ड डिपेंडिंग अपॉन द रिसीवर. और you can also check with, there is a formula, right? KTQ, depending upon what is the variance due to short noise. If the main source of noise is short noise, you can model it by some formula KTQ, where K is Boltzmann constant, T is the temperature in Kelvin, that you can check. Okay, so there is a physics behind that. So you can see that what is the variance of, for example, there is a hardware, right? So there is short noise due to random fluctuation of electrons. So as you know, it depends upon the temperature, right? It depends upon Boltzmann constant. The constant is K, so that formula you can check. ठीक है ना? हाँ. So yes, so as I said that at the receiver end, here you will get AI plus WI, and here also you will get AQ plus WQ, and both WI and WQ is 0 and not by 2, 0 and not by 2. Correct? I hope I make sense till this point. So now the question is, okay, now we have modeled the, अभी क्या होगा? For example, there is a particular case of, or okay, let's take this K phi 1 K cos 2 pi FCT, K sin 2 pi FCT, and this value is for example 1 1 1 minus 1, sorry, minus 1 1 minus 1 minus 1 and 1 1. This is the value, right? And we map 0 0 with this, 0 1 with this, 1 1 with this, 1 0 with this. ठीक है? So ये क्या है? This is a QPSK scheme. Why QPSK? Because there are 4 points. So Q means quadrature, and they are in quadrature in phase. Or it is PSK because all have same amplitude, but only phase is different, right? Why quadrature? Because there are quadrature in, the difference in phase is pi by 2. If you see, there are pi by 2 difference, right? Anyways, बोलो. हम्म 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 हम्म. नहीं, in QPS के power of each is same because power depend upon the this, है ना? We have discussed in the last class. So power is same in QPS. In PSK scheme, all the signals have same power. ठीक है? No, in QAM it is not. In ASK it is not, because it depends upon the distance from the origin. Here distance from origin is same, so all have same energy. So okay, so this the transmitter you have using. So for example, you send this signal 00 comes from your source. So what will you transmit? 1 times k cos 2 pi f ct and 1 time plus k times sin 2 pi f ct. And at the receiver, what will you get? 1 plus some noise and 1 plus some noise. Yes or no? After doing all of this. ठीक है ना? So after passing it through a box, which is a correlator filter, you will get this, right? This is phi 1t for you, and this is phi 2t. So you have implemented a correlator filter, integrated it, and you have found it. This you can, so together you can call it. This is Ri and this is Rq. Correct. Now your aim is to use these two values at the receiver and tell me what was transmitted. Ri is 1 plus Wi, Rq is 1 plus Wq. So you will have some value. For example, 1.4 Rq you measure, you have passed it through this, right? Here you will receive 1.4 and maybe 0.6. It can happen, right? Because Wi and Wq can take any value. As I told you that Wi and Wq are random. They are Gaussian. They will follow this distribution, but they can take any value in this. Yes, probabilistically it will be centered around this. More, the probability that it will have this or more, but it can take any value, right? So, for example, you have obtained 1.4 and 0.6. Means 1.4 will lie somewhere here. This is 1, so 1.4 here, and 0.6 will be here, right? So your received signal, if you just draw geometrically, will lie here. Yes or no? You have transmitted this, you have received this. It can you can draw it geometrically for the analytical purpose, and also you can draw the constellation diagram in the receiver. This is called receiver constellation diagram, right? What is the meaning of this? You have to just see, you have to project your R in phi 1, this is called Ri, and R, whatever you get in the upper branch is called Ri, whatever you get at the lower branch here, right? Ri, this is Ri, Ai plus Wi, and this is Rk. So you can draw it like this. Yes or no? So now by observing this, you need to tell me whether this was transmitted, this was transmitted, this was transmitted, or this was transmitted, right? So this is called detection problem. Do you think, I mean, as you are all well known with, I mean, all of you know this likely this ML thing, right? AI thing. So it is a detection problem, classical detection problem, yes or no? Whether it was transmitted, this was transmitted, this was transmitted, or this was transmitted, right? Okay. For example, you correctly say by observing this and applying some logic. So you are having R, which contains the upper branch and lower branch values, and you provide it to a optimizer which you have designed, which will give you either 1, 2, 3, 4. 1, 2, 3, 4. If your optimizer rightly said 1 and you have sent 1 from here, means you have sent this, for example, and your optimizer says this, map it with this, you receive this, and your optimizer mapped it with this, then you say there is no error, right? But if your optimizer, this optimizer function which you have implemented says no, it is closer to this, or it is, I mean, it decides in favor of this or in favor of this point, then you say that error has occurred, right? Yes or no? So the receiver performance, so by this discussion, we can come to the conclusion that receiver performance can be measured in terms of, batao, its error performance, right? Yeah. So your function should be such that its error performance is less. Best performance is good means error is minimum, right? You should try to design your F which minimizes the error, right? F, अभी तो F आपके हाथ में है ना. F is in your hand. We have not yet designed F, right? We are moving towards that. We only have those samples, these values, samples or the INQ components with you or the R with you. And now by using this R, you have to do that, right? So I will write one statement without proof that. So you have understood what is error, right? Error means if your received signal is not, or if your, I would say, estimated signal is not what you have transmitted, then you say that it is error, right? We have error. Okay. So I would write one statement without proof that maximum a posteriori estimator. So our job is to design estimator, right? This is the estimator, right? Which estimates by observing R what would have been transmitted, or what could have been transmitted, right? So maximum posterior estimator or maximum likelihood estimator. Spelling you can check, I think it's a posteriori. Okay, I will just write the correct spelling. Okay. Okay, so you all know this. So it will make my job a bit easier. I would quickly tell you what is MAP, maximum a posteriori probability, or maximum a posteriori probability estimator, or maximum likelihood estimator. This is a special case of this. Maximum likelihood estimator is a special case of this. What is maximum? I would just call map, right? Because this is a French term and it twisted the tongue, right? So map, what is map estimator, right? So you have observed R, and now your aim is to tell me what was transmitted, the X hat. You have observed R. So let's not denote it by F, let's denote it by G. because f we have used for PDF, right? So x hat is the g you have to use, and you have to design your g such that probability of x does not equal to x hat is minimum, right? So we say that g is map. You understood my point? This is your g which is asked that we should design the estimator g such that, हाँ बोलो, this is the error, right? This is x hat. X hat can be either of the four combination, four possibilities in this case, our case, and this x can be any of these four. ठीक है? So G is map. So what is map? I would just quickly write it. You have to evaluate your probability of all the possible access from R. You have received R. You have to find out what is the probability of x given R. That is why it is called a posteriori. Means after observing the signal, received signal, what is the probability of the transmitted signal x, right? So this, with this one, no, now we are defining what is g. So g must have, you should design your g such that, okay, one second. So this is your R, right? How would you design it? You have to take whatever R you have received. What are the possible access? Evaluate this function which is called likelihood function. All the possible access, and I call this set x to put all these possible access. For example, in this case, our example, what are the possible access? 1 1 minus 1 1 minus 1 minus 1 1 1. So in our case, special case which we are discussing, or toy example which we are discussing, your x can be either of the four: minus 1 minus 1 1 1 minus 1 1 and 1 minus 1. So you have to optimize or evaluate this likelihood function R, whatever you have received, then you have to evaluate, you have to see for which x this is giving the maximum value. Now this feels little tricky, right? Yes or no? कि कैसे करना है? Is it simple? Okay. How to evaluate this? The steps are as follows. Is this known to you or not? No, Bayes rule. By applying Bayes rule, you can write this. एक नीचे का डिनोमिनेटर भी रहता है. नहीं, अभी इतना ठीक है. This is Bayes rule, clear? You have to maximize or we have to write f because R is continuous. Where do we write probability? When we have a discrete random variable. See, this x is discrete, only 4 values, correct? but R is a continuous random variable, right? Because of the continuous nature of the noise. Noise is continuous, though you have transmitted this X, it can take any value, right? This plus this, right? You understood my point? Yes or no? So X is discrete because it can take only 4 values in our example, or a fixed value depending upon the constellation point, because X from the constellation points. But R is continuous, and for the continuous random variable we write PDF, probability density function, and for discrete we write probability. So just go through this. If you have doubt, you can. So X from here, right? मुझे एक बात बताओ, is this fixed or not? PDF of R, does it depend upon this? So from the maximization process, you can take it out. That is why. So this is your map. So now, if you want to know X set, what you have to do, you have to maximize it for all the possible X. And whatever X maximizes it, that is called argument. Argument that maximizes this, you can take it. So this is called map. Are we clear? Further, if all points in X are equiprobable, meaning that probability of X is depending upon the 1 upon cardinality of X. ये क्या है? Cardinality का क्या मतलब होता है? Number of points in the set, right? ये पता है आपको? For example, X में 6 points हैं या 4 points हैं, and all are equiprobable. This it means all are having probability 1/4. So if I have a set X with 4 possible elements and we call it that they are equiprobable, it means probability that each xi is 1 upon cardinality of X, that is number of elements, in this case 4. ठीक है, ये clear हो गया? So if all points are equiprobable, does it make any difference? Because if whatever X you take from this set X, it will have equal probability, right? So if in this particular case, when all points in X or the constellation are equiprobable, then your X hat map will become, bolo, probability of R given X. This is called maximum likelihood. So यहाँ पर एक there is a small correction. Here I said that this is a likelihood, right? So just erase it. Actually, this is likelihood. Correct? This is a posteriori probability or a posteriori function, right? Map. Please correct it. Abhishek, is it? Do you have any doubt till now? Subtle points you can check, but more or less, I mean, things are clear, right? Please ask if you have any doubt. Map says that you have to maximize this function, which is called FSCDF, probability density function of X after observing R. ये ठीक है? That is why it is called a posteriori, after observing R. What is the probability of X? So, for example, you have observed some R and you need to find out which X was transmitted. So, you have to evaluate this function. Now, how to evaluate this function? You will apply Bayes rule and it will further reduce to this point. अभी क्लियर है कि नहीं? यहां तक क्लियर है? बोलो भाई. Okay, so let's see how you are going to apply this to our example of this. यही तो करना है ना? As I said, you can have this Ri and Rq and you need to tell what was transmitted. So you have to apply this function. So the problem is how to evaluate f of R given X. Note that this is likelihood and this is a posteriori probability function or a posteriori PDF of X given R. Or I would say I should call it probability because X is random, right? Sorry, it's discrete, right? So what is the probability of a particular X for after observing R? So you can use this. So just make a, and this R is continuous. This is continuous. That is I would always use PDF. Yes. Yes. Now it is correct. There is a subtle point that X is discrete, right? X can take only these values. So see, initially there was some probability, right? आपके पास you had 4 points, right? You had some probability that what was the probability of transmitting x1, x2, x3, x4. And what is x4? This vector. Once R can be either x1 plus wi wq, R is a two-dimensional vector. I mean, you can put upper branch and lower branch values Ri and Rq like this, right? So this is your x1, which will have these two values, I value and q values. Similarly, R2, R3, R4. So I have just written it as R is equal to x plus tau. This x is this. I mean, initially, what was the probability that of transmitting this? This depend upon the. It will depend upon the probability of occurrence of 0, 0, 0, 1, 1, 1, and 1, 0. And in general, it is same in general. But after observing R, what would have been the probability of some particular x? That is called a posteriori probability. So, I mean, once you know this, you can say what was the more likely event. You can think like that. You understood my point? Okay. Let's. I hope you have made this correction that this is probability because x is discrete and this is R, so it is PDF because R is continuous. And why R is continuous? Because R is x plus noise and noise is continuous, so R will also be continuous. So this is maximum likelihood. Okay. Okay, let's try to solve this. Rather than going to F, we assume that all points are equiprobable. Please let me know if you have any doubt. We will stop and discuss. So this is called likelihood. आपको क्या करना है? What is your aim? To maximize it for all possible access and take the argument which is maximizing, and you call that was your x hat. But what is this PDF of R given X? Okay, so for this, what is your R? Please tell me. Abhishek? Very good. So it is X plus noise, which is continuous. But once you sample it, this is R is equal to X plus N, right? I mean, okay. So R is a sample that I think you understand, right? Why I'm calling R as continuous, right? Because N can take any value, so R at any given time can take any value. That is why I'm calling it continuous. Okay. So if you have studied your signal processing or statistical signal processing, tell me what is FR given X. नहीं नहीं वो तो वो तो F ये निकाल लिया ना हमने. This we have simplified to this likelihood. Now our aim is to find out this likelihood function. This is called likelihood function, and this is called a posteriori probability. When X given R, this is called a posteriori probability after observing R. But this is difficult to derive, or if you want to derive, we have to use this formula. Okay? So we have further reduced it, and we have further assumed, which is practically correct, that all the symbols are equiprobable. Most of the time it is. So we have reduced our map to ML. Okay? What was the map? We have to maximize probability of X given R. Now you have to maximize R given X. अभी ठीक है? What is the PDF of R given X? So I will just write it is PDF of noise, which is mean zero and variance sigma square. We already know it. Okay, let's because 2. Okay, let's do it separately. Okay, so F of R given X, right? R is 2 in phase and quadrature phase, right? ये सही है कि नहीं? ठीक है. Both are independent. In phase पे dependent है. The in phase received signal only depend upon the what was at the in phase xi. Similarly, what you receive. Okay, just one thing. Here, this is Ri is depend upon Wi only. Rq depends upon this part only. I mean, what was present in phase or quadrature phase. So you can further write it like this. Ri is xi plus Wi. Rq is xq plus t, where Wi is n naught by 2. ठीक है ना? यहाँ तक क्लियर है? So up now the question is, what is the PDF of Ri given xi? तो अभी मैं बोलूंगा भाई randomness in Ri given xi is only due to wi? Yes or no? So PDF of Ri given xi is same as PDF of this random variable. Yes. Evaluated at Ri minus xi. देखो मैंने क्या बोला तुम्हें आर आई क्या मिला था यू हैव रिसीव्ड आर आई एज 1.2 in our example, right? You need to find out what is the probability or the sorry PDF of Ri given. For example, अभी इस पे देख रहे हैं राइट आपके पास 4 पॉइंट है ना xi for this you need to know what is the value of this function, right? This function is, I would say, because you have observed Ri given xi and Ri and xi are related like this. So if you say that xi is given, the randomness is only due to wi in Ri. So PDF actually when you do this signal processing course, they tell all of these things, right? How to find out the PDF of if x is a random variable, what is the PDF of ax plus b? So I'm not going mathematically. I'm just telling you intuitively that if Rxi is given to you, what is the PDF of Ri given xi? Whatever is the PDF of wi, evaluate it as Ri minus xi. Understood my point? If this is the case, ये क्या है? This you know? Very good. Let us say that. But 1 upon root 2 pi sigma square. I'm just writing it sigma square. Later we will replace it by n not by 2. Exponential of minus बताओ w क्या है वैल्यू क्या है w की माइनस एक्स वेरी गुड एंड मीन इज 0 upon 2 sigma square. I am using here only this formula which I have just written, right? Yeah, this one. W is in our case Ri minus xi. Further simplify it 1 upon root 2 pi sigma square exponential of minus Ri minus xi whole square. ठीक है as I told you what is the PDF of R given xi which is same as PDF of this evaluated at Ri minus xi. So ये भी पता लग गया. Similarly you know this, you can evaluate this. So similarly RQ given XQ will be बोलो W evaluated at RQ minus XQ. Same you can write, same ही होगा. It statistically just this will change. ठीक है correct up to this point. Now I can write my f of likelihood of R given x. R क्या था? It is a Ri or RQ combination. X is a combination Xi XQ. You can also write it in vector. So product of these two, what you can write? 1 upon root 2 pi sigma square into exponential of बताओ minus Ri minus Xi whole square and exponential multiple. We are just multiplying these two. So once you multiply this, exponential of this, multiply this factor I have already multiplied, so square. Correct? Exponential of, add it, because exponential of a into exponential of b is exponential of a plus, yes. Yes or no? Now your aim is you have Ri, Rq, you have all the possible Si, SQ, evaluate this value and tell me which gives you maximum value and decide in favor of that. So what you have to do? You have to maximize. This is a constant, has nothing to do with the maximization. Yes or no? This was our aim. Please let me know if there is some doubt, we will discuss. This is some constant which has nothing to do with varying x. This will be fixed. Only this part will change, right? Exponential of minus Ri minus xi whole square plus rq minus xq whole square. ठीक है ना? So you can take it out or you can ignore this term because this does not contribute in the maximization process. Our aim is to find out x hat. तो अभी मुझे बताओ, you are maximizing this, right? Abhishek, can I write it like this? Distance between r comma x whole is square upon 2 sigma square. Yes or no? What is this quantity? R is Ri, Rq, x is xi, xq. So what is the distance between r and x? Under root of this? हाँ, नॉर्म कह लो या फिर नॉर्म तो एक वेक्टर का होता है ना, बट देयर आर टू थिंग्स r and x. अरे डिस्टेंस, ये एक वेक्टर है, ये एक वेक्टर है, इनके बीच का डिस्टेंस क्या हो? व्हाट इज द डिस्टेंस? अंडर रूट? ना ना, okay, okay, don't worry. I have a point 3 comma 4, there is a point 2 comma 1. What is the distance between them? 3 minus 2 whole square plus 4 minus 1 whole square under root square. So this is what I am saying. Now it clear? Okay, so this is my, this is the example. Okay, so now your x hat ml is this. That whatever r you have received, you just need to find out the distance of that r from all the possible x. But there is an exponential here. Exponential is a decreasing function, yes or no? Exponential of minus, sorry, because it is exponential of minus of this. If you want to maximize this, you have to minimize this exponent, yes or no? Because e to the power minus 2 is greater than e to the power minus 3. This is e to the power minus x curve. This is x equal to 0, this is 1, this is 2. E to the power minus 1, e to the power minus 2, yes or no? If you want to maximize this quantity, what you have to do? You have to minimize this exponent, yes or no? If you want to maximize this complete thing, okay. So if this exponent is less, yes. So what you can write, arg min x in x d of r comma x whole square, and whole square will also not make any sense because distance is always, I mean, if distance is less, then square will also be less, right? Okay, chalo, kar lete. This will not make any difference. Square will not make any distance, any difference. So can we write it not or not? Yes or no? Okay. What was our question in hand? We had 4 points, 1 1 1 minus 1 1 minus 1 minus 1, and what was that point? 1 minus. This was our transmitted constellation diagram, and I told you that we have transmitted this, for example, and we have received this 1.4 comma zero point 0.6, right? This you have received. Now tell me what was transmitted. What will you do? You have to evaluate this function. What you have to do? First, this is your r. This is your r. Evaluate distance of r with this point, distance of r with this point. Karo 1.4 comma 0.6 with 1 comma 1. What is the distance? 1.4 comma 0.6 with minus 1 1. What is the distance? Evaluate it and tell me fast. Your aim is to design an estimator which just observe the R is the RI, RQ, and tell me what was transmitted. So we started with the map. We said we use map. Why we use map? Because it minimizes the probability of error. Though we are not seeing the proof, but we are taking as a statement that map minimizes probability of error. Then we have moved towards ML. From map, our symbols are equiprobable, and we have also seen that in this ML, this was our ML, right? This ML becomes minimum Euclidean distance decoder. Okay, just do it first. Otherwise, it will be a bit heavier for you. So whatever R you have received, our aim is to find first is distance from all the possible constellation points. In our case, in this particular example, we have 4, so we will find out 4 possible distances. Now, अभी मुझे बताओ, if this value, for example, कितना आ रहा है बता दो, please fast. 1.4.56. Second one, approximate, just tell approximate. Because you don't know ये R आपको किससे मिला है. You don't know which constellation point you have transmitted, either 0 0 0 1 1 0, or this is 1 1, this is 1 0. You don't know, na? You have just received R. At the receiver, you don't know, because at the receiver you don't know what was transmitted at the transmitter end. Yes or no? Why it is something like that? You have 4 daughters, for example, or 4 kids. Somebody shouts, right? You just listen. You have to make out which one of them has shouted, right? So it is something like that. You don't know which transmitter has symbols, right? Which symbol was transmitted at the transmitter end, but you just know at the receiver you have applied some RIRQ sample, and then you put it to the estimator, and that estimator is ML, which says evaluate the distance. इसकी 0.56 है दूसरे की 2.56 third. I think it will be more, three, more than three, and it will be also be around two, something like that. Okay, two. Last one or this one? So what you have to do, you have evaluated the distance. Okay, now tell me, maximizing this, you put all these three values. Exponential of ठीक है ना, exponential of minus 0.56, exponential of minus 2.5, exponential of minus 2.3, exponential of minus. Which one is maximum? This one. That's what I'm saying. Don't evaluate exponential. Just see the minimum of this. Rather than doing argmax, what you can do? You can do argmin, because the exponent which is minimum will give you maximum value. It is due to the nature of exponential of minus function. Now you understood my point? I hope now you appreciate. Maximizing this, that you have exponential function divided by this sigma square, which is constant, will not make any difference. So maximizing this will give you this, and which is same as that you minimize this. The argument 0.56, 2.5, 2.3, 1.5. This will give this, right? So it is the same thing. So why not just minimize the argument? It is called minimum Euclidean distance decoder. Why Euclidean? I mean, it's a minimum distance, and Euclidean is distance decoder. Euclidean means x1 minus x2 whole square plus y1 minus. Actually, there are various distances which are defined in the literature, but this is the natural distance which we use in order to evaluate the distance between 2 points, and which is called Euclidean distance. Please go ahead. Yes. Yeah, please. So अभी for a given R you can easily find out. तो अभी मुझे बताओ. There is a binary case. क्या केस है? BPS के. ठीक है? There are two constellation points. This and this corresponding to 0, corresponding to 1. ठीक है? Now, how would you decide? I mean, there is some, you will transmit either this or this, right? So at the receiver, if your R lies here, oh, because it's one dimensional, so there is no Q part, only I part. So if your R lies here, it is closer to 1, yes or no? Yes. Now we have found out the estimator. The estimator is the minimum distance estimator. See, the whole mathematics which we have done, it's for the reason that we wanted to know what X was transmitted by observing the R. Do you appreciate this or not? So what we have concluded, that if R you receive, sorry, it's a one-dimensional constellation. So if you R you receive is closer to x1, then you will decide in favor of, otherwise you will decide in favor of x2. So if you just make a line, what is this line? No, just you are dividing this, right? So if your R lies here, in this part you will say x1 was transmitted. If it lies here, you will say, it means R is greater than x1 plus x2 by 2. x1 क्या है? In this case 1. x2 क्या है? -1. No. That is logic bit. So don't confuse it. Transmitted signal. We are transmitting about x, not bit. So 0. It means if R you receive for binary, it is for binary BPSK. Now we have come up with the concept that if you want to know the x by observing R, we will find out the distance of that R from all the possible constellation. So now we are starting with BPSK. You have received some R. When will you decide whether x1 was transmitted? When R is greater than this quantity, midpoint, which is 0. So if R you receive is greater than 0, then you decide in favor of logic 1 or x1, or otherwise you decide in favor of logic 0 or x. So this will become a threshold defect. Simple. In case of binary, your minimum distance decoder is a, अभी आपको डिस्टेंस भी निकालने की जरूरत नहीं है. नाउ यू डोंट नीड टू फाइंड आउट द डिस्टेंस, यू कैन जस्ट कंपेयर योर आर विद द थ्रेशोल्ड. यस और नो? Zero is called threshold. Why we are calling it threshold? Because if your R is greater than this threshold, you decide in favor of 1, otherwise you decide in favor of 0. You can also evaluate R with distance of R with x1 and distance of R with x2, but it will unnecessarily consume your computational power. Yeah. It is same as if R is greater than 0, it is closer to this. If R is less than 0, it is closer to this, because it's one-dimensional thing, right? Okay. Now, let us take an example. We have 3 points. This is our constellation. एक और कर देते हैं. हाँ बोलो. Okay, okay? Have we exceeded the time? Because okay. So what is the time currently? 1:40. To give me 10 minutes. Huh? Is it okay? Yeah. Just 10 minutes. Just we'll do this example, or rather numerical. So at the receiver, I have received 0.9, 0.6. You understood my point? My receiver is something like that. Bank of correlators. Here I have received 0.9. Here I have received 0.6. This is Ri. This is Rq. Now tell me what of which one of this symbol I have transmitted. First, assuming the noise is Gaussian and additive. Here we get xt plus mt. And noise is Gaussian additive. क्या करोगे बताओ? Yes. So you will find out, you will evaluate distance of this R with all the four signal points. Very good. Yes. 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 Correct. So you will decide in favor of that signal point. So please do it and tell me which one is the closest. Whatever we have done is this, that if your noise is Gaussian and additive, how you are going to evaluate the, or how you are going to estimate what you have transmitted. What you have to do, you have to evaluate the minimum distance from received point to the all the signal points, as you correctly said. Which one is the closest? R will be something here, 0.9.6 here. I think this one, right? So this, no, 0.9, 0.6. Yeah, distance, right? Okay. You have evaluated distance of R with this. I think this will be the nearest one. So the whole maths what we have done is this, that when your noise is Gaussian and additive, we have found out that you have to evaluate, you have to design a minimum distance decoder. Means you have to evaluate the distance of your receive point with the signal points. Understood? Okay. In the next class, we will just quickly see the one or two topics which are left, and then that will be our last class. Okay. So if you have any doubt, please ask anyone.